Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to finally have a chance to play around with those chemical formulas and kind of see their use. So there's a lot of different things we can do with a molecular formula. Biggest things, we can start playing around with a lot of physical properties we've seen so far. So one of the important ones that we've run into before is the molar mass of a species. However, in order to calculate the molar mass as we've seen before, you need to know its composition. And once we have the molar mass, any conversion in between the mass of substance, the amount of substance is possible. And you can do a lot with that. So one of the go-tos is you can pair your molecular weight with Avogadro's number to try and determine the number of molecules present uh, in a system, or even the number of atoms of each element present. And we've played around with this already so far. Another thing you can do is you can combine molar mass and density to find the number of molecules per volume of substance, or if you know the number of molecules, you can figure out the volume present. So by pairing these three together, volume to mass, mass to moles, and moles to number, we can actually do a lot of conversion up and down this sort of spectrum. Another thing we can do is relate our use our chemical formulas to try and determine those mass percents of an element in a given chemical species. And we've already played around with these ideas a little bit in nitrate. But now we can use this idea of the molecular formula. So the basic idea of the percent weight of a substance present is we can figure out the mass or atomic weight of the weight of element X in 1 mole of species. And then we can divide this by the total mass of the compound in 1 mole. Well, we know this one, it's simply the molecular weight of the compound, which we now know how to calculate. The little bit trickier one is the mass of element X in 1 mole. Because unfortunately, for a lot of different compounds, we may have more than one atom of element X in a given species. So we have to pair together the number of atoms of that element and that atomic weight paired together, and we get the total weight of a given element on 1 mole of species. So for example, if I'm looking at carbon dioxide and I want to find the percent mass of carbon dioxide, I have to take I've got two atoms of carbon dioxide in the compound, and the atomic weight of oxygen is 16. And then I can divide this by the total molecular weight of the compound, 44, and this will give me the percent mass. This also gives us another way to get to those experimental masses that we talked about last time. That, as we saw, was really how early chemists first started determining what molecules were what, because they gave us those empirical formulas. So we can use this, again, molecular formula for CO2 to calculate the mass ratios. So for example, if I've got 1 gram of carbon, I can figure out the mass of oxygen. First, we can go ahead and go through our unit analysis, grams of carbon. So I can use the molecular weight of carbon, then the stoichiometric ratio. I have twice as many atoms of oxygen as I do carbon. And then I can use the atomic weight of oxygen. And if you watch out, you can simply cross out all of the various elements. And we find for every 1 gram of carbon, there should be about 2.7 grams of oxygen present. And again, this is the exact number that was originally used to define what CO2 was before they ever even knew what an atom of carbon or an atom of oxygen was. These are those definite proportions. However, it's also possible to kind of go the reverse way. If I have a mass ratio, I can determine the molar ratio. So let's go ahead and take a look at glucose. So glucose has a mass carbon to oxygen mass ratio of 0.75 to 1. So again, more mass of oxygen than carbon. So I can do a similar analysis, set up the ratio of atoms, and then I can go ahead and convert grams of oxygen to moles of oxygen using the molecular weight, and the same thing with carbon. So this gives me as I walk through a ratio of moles of carbon to moles of oxygen. And lo and behold, it's a 1-to-1 ratio, meaning there's just as many, a glucose molecule has just as many oxygen atoms as it does carbon atoms. However, this simple mass ratio to molar ratio doesn't give me the full molecular formula of glucose. For that, I need to go a little bit more complicated and going to a full mass percents to an empirical formula, which we'll go ahead and tackle next time. Until then, take care.